Welcome back to The Explainer. Today, we're taking a journey deep, deep underground. We're going to explore a completely hidden world to answer a really fundamental question in energy. How in the world do you get liquid to flow out of solid rock?
So here's our roadmap for this journey. First, we'll talk about this idea of an underground sponge. Then, we'll look at the 3 types of fluids you find down there. After that, we'll get into flows, regimes, and how time changes everything. We'll also cover the actual shape of the flow and then put it all together with the master recipe, Darcy's Law. And finally, we'll wrap up with why any of this actually matters.
Okay, let's dive right in. The first thing you have to wrap your head around is this kind of surprising idea. Solid rock can act just like a giant sponge.
Look, we all get how water flows through a pipe, right? You can see it, it's simple, it's totally predictable. But getting oil out of a reservoir, it's the complete opposite. It's happening thousands of feet below us, through this incredibly complex maze of hidden pathways. It's completely invisible.
And you have to forget any image you might have of these huge underground caves filled with oil. That's a total myth. The reality is, well, it's a lot more like a massive, solid rock sponge. It's filled with countless microscopic pores, and all those tiny little spaces are connected, holding the oil and gas.
So this brings us to the core challenge, right? For engineers, this is the whole game. How do you possibly predict, let alone control, a flow that you can't even see? I mean, where do you even begin?
Well, you start by breaking the problem down into its most basic parts. And the first piece of that puzzle is getting to know the fluids themselves, because not all of them act the same way when you put them under pressure. The key property here has this really fancy name, isothermal compressibility. But don't let that intimidate you. All it really means is squishiness. It's just a way to measure how much a fluid's volume shrinks when you squeeze it. That's it.
And using this idea of squishiness, engineers basically divide all reservoir fluids into 2 main categories that we see in the real world. You've got your slightly compressible fluids, like water and oil, and then you have your highly compressible fluids, which is basically all gases.
And you got to see the huge difference in how they behave. If you crank up the pressure on oil, its volume, it barely changes. But you do the exact same thing to natural gas, and whoa, its volume changes like crazy. And that distinction, it is absolutely critical for figuring out how a reservoir is going to produce.
All right, so we've got the fluid squishiness down. The next big ingredient we need to throw into the mix is time. We have to understand the reservoir's changing heartbeat as we start producing from it.
And this heartbeat is what engineers call a flow regime. It's just the pattern of how a reservoir's pressure changes over time as fluids are pulled out. It really tells the story of what's happening in that hidden world, deep underground. You can think of this graph as being like an EKG for the reservoir. Seriously. By tracking the pressure over time, we get this diagnostic readout of its health and exactly how it's responding to what we're doing. So let's take a closer look at what these different lines are telling us. So each one of these lines tells a completely different story. That flat steady-state line, that means the pressure is holding strong. Maybe there's a big aquifer pushing back. The steep unsteady-state curve, that's the initial shock to the system when the reservoir first feels that withdrawal. And then the straight, declining pseudo-steady-state line, that tells us the entire system is now draining at a nice, predictable rate. So we have the fluid, we have its behavior over time. Now let's think about the physical path it takes to actually get to the well. Because when you're talking about a reservoir, geometry is destiny. A well is basically a tiny little straw stuck in a giant rock sponge. So naturally, the fluid is going to converge on it from all directions, 360 degrees around. This is what's known as radial flow. The easiest way to picture it? Just think of water going down a drain.
But what if you could kind of hack that geometry? Well, engineers do that all the time. By creating a hydraulic fracture, which is basically a long man-made channel in the rock, they create a new path of least resistance. And now the fluid flows in these neat parallel lines straight into that fracture. That's called linear flow. So the main point here is that the physical shape of the reservoir and the well, those aren't just minor details. They fundamentally dictate the path the fluid is going to take. And understanding that geometry is absolutely key to predicting the flow.
Okay, so we've got the fluid type, we have its flow over time, and we know its geometry. So how do we pull all these ingredients together into one single, powerful recipe that describes this whole process?
Well, the answer is Darcy's Law, something figured out way back in 1856. And at its core, it's a surprisingly simple and intuitive idea.
It basically says the speed of the flow depends on just two things: how hard you're pushing it and how easily the rock lets it through.
And this table here kind of shows the components of that recipe. Velocity, how fast the fluid moves, is all about the pressure gradient, which is the push. But that push is being fought by two things: the rock's permeability, which is how easily it lets fluid pass, and the fluid's own viscosity, its thickness or stickiness. This is the master equation for everything we've just talked about.
So why is all this important? Why should you care? Because this isn't just theory in a textbook. Understanding this recipe, this is the key that turns a bunch of rocks into the energy that powers our entire world.
You see, by mastering these principles, engineers can do some pretty incredible things. They can accurately predict how much a well is going to produce. They can manage the reservoir to maximize how much we get out of it, and do it all with as little waste as possible.
By figuring out the physics of this hidden world, we are literally able to power our own. It's just a powerful reminder that these complex, invisible systems are all around us, governed by these elegant, simple rules, just waiting for us to understand them. Which really makes you wonder, right? What other invisible systems are out there, all around us, just waiting to be explained?